So wonderful lecture as always, Yury. So there are several questions. I will take up a few, within this time that we have. So basically, for the synthesis of MXenes. So one question was, what are the most difficult parameters to handle, and can a single layer be prepared or not?
Yes, of course. Let me start from the end. We can prepare single layers. The ones that I showed you in silicon wafer, those were single layer flakes. We can go now approaching now 100 micrometer size and definitely can make a reliably large quantities of 50 micron flakes. Even so, for most practical application, few micron flakes are sufficient. Moreover, this like liters of solution I showed you, colloidal dispersions, are based on contain single layer flakes. So definitely yes. I cannot say that there is a single most difficult problem in synthesis. It is just variety, because it looks easy when I tell, look, we can prepare hundreds of different materials, but it takes several months to optimize synthesis for each of those. So we need to control all the parameters I showed to you, controlling kinetics, temperature, type of etchants, time of etching, ensure that we don't create defects in this etching process, and many others. So it's all about this variety, but that's exactly why it requires entire community. No single lab can accomplish it all. And that's exciting because there is so much research that can be done and plenty of room for discovery for everyone by finding mechanisms of synthesis and processes to synthesize new MXenes.
Yeah. So the next question I'll take up is, does thickness degrade the properties, and are they stable at the ambient atmosphere? This particularly for the high entropy MXenes.
We have done very little studies on high entropy MXene. They seem to be okay, but naturally some of the elements may oxidize, for example, or hydrolyze faster than others. For titanium carbide MXenes, we have samples made 10 years ago, films which still keep their conductivity. In solution, if they are stored in a closed vial, they aerated in the refrigerator, titanium carbide, niobium carbide, you can keep probably for a year. Some other, like a V2C, titanium 2C, degrade faster, preferably use them within weeks at maximum. Now, thickness actually doesn't degrade properties. Moreover, add some properties. Graphene is flimsy. Thicker MXene layer have much higher bending rigidity. So you can get flakes which are really flat in films, composites, which actually allows you to achieve, for example, high mechanical properties, better alignment. So it all depends what kind of properties you are interested in.
Very related to this layering, there was a question like, for this XRD characterization, do we always see the 00L planes, and is there any other planes or that we can see for in these systems?
Yes, you primarily see 00N planes, because if you have a film with flakes aligned, you will only see pretty much interlayer distances. Now, when you have random orientation, you can still see a lattice parameter measure. For example, for titanium 3C2, it will be a peak in copper KF radiation at about 63 degrees. If you want to really properly study the structure, you need to go to pair distribution function analysis rather than powder diffraction.
The next one is I will take up is, can we make single crystalline MXenes, and do we need gentler methods to achieve the long range order?
All MXene flakes have long range order. Pretty much all of them are single crystal. So whenever you see single layer flake, it is a single crystal. Of course, in multi-element, particularly high entropy MXene, you can have random arrangement. So you can look at them as materials with no long-range order at the atomic level, but still two-dimensional structure and order out of plane because they're layer by layer, and there you have carbon and nitrogen layers ordered here. So, but in general, yes, those are single crystalline material, what makes their modeling easier because they have periodic structure and they have small thickness. So even DFT can be done with a relatively low cost compared to carbons.
Okay. So when there is HF etching or this LIF HCl with etching, the best the MXenes are obtained, but they are toxic to handle. And during HF etching, how to prevent oxidation of the MXenes?
Well, oxidation you prevent by ideally etching in a deaerated environment, like you can bubble nitrogen or argon. But in general, just a regular etching will not lead to oxidation if you have a stoichiometric max phase precursor and if you don't over-etch. That's why I focused on kinetics. You need to know your kinetics, that you don't keep it for 24 hours if the process ends, in fact, in 2 or 4 hours. You need to keep temperature constant to ensure there are no variations. We do it, for example, usually at 35 degree C, purely to ensure that it won't be day, night, winter, summer temperature variations here. But yes, you can definitely produce material of good quality by etching in HF solutions, but lower is HF concentration, more stable material will be, fewer defects you will get.
So is there any alternative to this HF etching, a more environmentally benign method which can produce good MXenes?
Yes, of course. I showed to you, for example, molten salt, LAMS method is used very widely around the world nowadays. We do gas phase etching, something very similar to making carbide-derived carbons that my group was exploring for more than a decade. There are also ways to etch it in bases and also in various salts. However, we know less about properties of those materials, so since we don't do it in my lab, I won't tell you what is the level of properties. But using lithium fluoride or sodium fluoride and HCl or even acetic acid, you certainly make materials which are non-toxic. We have done together with collaborators very detailed studies of stability and cytotoxicity, blood compatibility, genotoxicity of titanium, niobium, tantalum, carbide MXenes. And if you wash them well and remove residues from etching, you get materials that are non-toxic and can be safely used.
Yeah. So related to this oxidation, which you have you just addressed, there is a related question that TIC gets converted to TiO2 during this electrochemical reaction. So what type of MXenes can show good electrochemical stability in all the like from alkaline to the acidic pH?
Sticker MXene, niobium MXene, tantalum carbide MXene, some mixed MXene. We observed they have pretty good stability even under positive potentials. All MXenes have very good electrochemical stability under negative potential. In general, they are typically very stable in acidic solutions and somewhat less stable in basic solutions. Again, MXenes like vanadium carbide, for example, V2C, that forms soluble compounds in both acidic and basic environments definitely will be much less stable. Titanium carbide MXene, tantalum carbide MXenes are much more stable because they don't easily form soluble compounds or form compounds with very, very low solubility. So in general, as a rule of thumb, thicker layers, M4C3, for example, MXenes are always more stable compared to M2C MXene with the same transition metal on the surface. And transition metals that have higher stability, lower solubility, give you, again, higher stability.
Yeah. So I'll just move to applications a bit. These defects like the metal vacancies, they reduce the structural, the stability and the electrical conductivity. So how the defect-induced MXenes can be used for batteries and the supercapacitors?
Well, again, for example, we cycled titanium 3C2 in sulfuric acid supercapacitor for 500,000 cycles with only 8% loss in their performance. We have materials like, you might have noticed, PhD students that I showed to you demonstrating MXenes, they had black lab coats for a very simple reason, because MXene once get on fabric, virtually impossible to wash away. It doesn't matter at what temperature, how you do it. For example, I have here a pocket square with imprinted by screen printing MXene names, and another one with 3 different MXene. You see 3 different colors. They all were printed like by my graduating student gave me as a present over 3 years ago. And they look just fine, and they are conducting, and they show different infrared signature just the beginning. So MXenes, after processing, have quite a good stability, even if there are defects internally. But it's all relative. There are different levels of stability. And definitely MXenes are more stable compared to a large variety of other non-oxide 2D materials that people use.
Yeah. So a related question to what you said, that the scroll has shown the superconducting, like the behavior. The question is why?
Very good question. We don't know, but it has been predicted that strain, for example, can significantly change electronic properties of MXenes. For example, for semiconducting MXene, switching from indirect to direct band gap, making some metallic MXene semiconducting, so on. So our assumption, this is a result of strain developing when materials is scrolled, because actually scrolling happens because of strain. But we need, or someone needs to model this behavior and provide an explanation to this. It's also important to stress, we still don't know really what is possible. We learn lots of things. As I mentioned, many theoretical predictions have not been even experimentally checked yet. So I think that's what is exciting, and that's why I actually checked this recent review in Nature Reviews Materials. We try to outline open questions there that require attention of the community, and I hope someone can provide answers to or explanation to the facts that we observed. This is an exciting field. There are many opportunities. There is so much to discover in the MXene field that I encourage everyone to pay attention to these materials and look through the prism of your knowledge, your expertise, your interest, how you can use them in your research, how you can contribute to MXene research. Thank you very much.